In today's video, we're going to talk about transducer fundamentals, including the piezoelectric effect, how beams are formed with ultrasound, and then talk about the different crystal layouts that give us just different transducer types. I show you here a picture of a dog with a squeaker toy because the piezoelectric effect uses an electrical current to squeeze a crystal and it basically spits out sound, much like your dog squeaks a squeaker toy and produces sound. And so this is just another diagram showing that if you pump electrical current into the piezoelectric crystal, that you get sound that's sent out from the crystal. The other critical part of this is that if you have a sound signal that comes back in to the crystal, when the crystal vibrates, it actually produces an electrical current. And because you have something that transmits and also receives, it's called a transducer. So this is the most basic element of any ultrasound transducer, is one crystal that has sends out sound when it has an electrical current applied to it, and then when a sound wave comes back and hits the crystal again, it produces another electrical current. So how does the ultrasound machine actually take all of these beams and echoes and turn them into an image? Well, essentially what the ultrasound machine does is it scans across the field of view with numerous different ultrasound beams and takes the echogenicity pattern or the reflection pattern from those and puts those together, stitches them together into one cohesive image over the field of view. So initially the ultrasound machine sends out a beam along the blue line, and then the next one next to it, and the next one next to it, and the next one next to it, and the next one next to that, eventually until you've built the whole field of view by sweeping across with different sets of echoes. So you have to have some way to organize these different sound waves and actually be able to produce an image. So originally what they had was what they're called a mechanical static transducer, where you actually had a gantry that had a single piezoelectric crystal transducer mounted on it, and that scanned across the patient in order to get the physical data about where a particular sound wave was and with respect to the patient, and that's how the beam lines were actually organized into an image, the individual beam lines. And those were from a physical correlation from the gantry giving you this image. And one of the things that I think that's neat about this image is it actually shows you that with the mechanical static transducers, you actually had a much broader field of view than what you have with our current electrically steered transducers. The next invention along the chain was a real-time transducer, and this meant that the image was actually generated at the same time as the transducer was scanning. It actually had a mechanical arm, which you can see here is the black portion with a single transducer element on the end, and the transducer and mechanical arm actually would rotate and scan back and forth so that you could see the image, and that's how you created the different beam lines that it required to make the image. And this is just a picture of one of those mechanical transducers. You might still see these in some of the smaller, just straight vascular access. Things like this is a site right, or maybe some of the older sonocytes where you actually still have that little stick with the transducer element wiggling back and forth on it. Our modern transducers, however, have a series of crystals that have beam lines that are electronically steered due to interference patterns in the sound waves that are created by each of the crystal elements. This is known as a sector or a vector type transducer, and I'd just like to contrast that briefly with the linear form of transducer. In linear transducers, you have many more individual piezoelectric crystal elements, and the beam, instead of utilizing interference patterns and firing them all at the same time, it actually selects a subset of the crystal elements that are physically located next to each other in the ultrasound array, fires those sequentially to form the first beam line, then augments over one for the second, and augments over another for the third, and so on for the entire length of the array. And this is the best current architecture for ultrasound transducers. Many of our transducers, even if they have a curved surface, actually have a linear array of crystals that are just bent along that curved surface. So curvilinear and linear transducers generally give us the best resolution over sector vector transducers. That about wraps it up for today. We talked about the piezoelectric effect, where electrical current can be turned into sound and vice versa. We also talked about how multiple crystals can be put together to form an ultrasound beam, and we talked about the different types of transducers with linear arrays and sector transducers.